What's that?
Not to say he's going to make it.
Oh, he's not going to make it. All right, messed up his perfect attendance this term. Okay, so we are now recording, and Matt, if you were in the linear algebra class, remember it didn't have any PowerPoints, neither does this one. So I have to do everything from a blank page or a graph, but we don't use graphs that much in here. I'm trying to get this to open, but it's having trouble opening. PowerPoint is just really a lousy system. Okay. Let me go over that last announcement. And the reason I'm doing this on Screencast-O-Matic is at least one of the students has not paid. But he hasn't been here yet either, but he told me he was wanting to do it via the YouTubes, okay, which we're trying to get to opening. We can't. And by the way, let me also say this. I don't have your syllabus updated yet. I think most of it's done, but it's not finished, so I don't have it on Blackboard yet. I do have the research paper updated, instruction updated, but I don't have those on Blackboard yet either. I have my locator card updated, but I don't have that on Blackboard yet either. I hope maybe this afternoon. I'm going to stay late and see if I can get as much of that done as possible. I got a lot to do, so I don't know if I'll get it all done or not, but I'll try. Next. Oh yeah, the link for Math 238. I've got the playlist set up, and I think the first class is in it, but I don't have the link established yet. So as soon as I establish the link, that'll be on Blackboard as well. Okay. Now, the last thing, one person's not here, hasn't been here yet, but that person hadn't paid yet. I wanted to say this in case he's listening to it through YouTube. They said they were going to remove all unpaid students last evening. I don't know if they did or not. Do you know if you got your
Yeah, I got on strike.
Okay, good. All right. Because I knew you did drop out, and I didn't know if that messed things up or not. I didn't think it should have, but it could have. So anyway, if you don't find out you're not showing up on the roll anymore, that's why. I'm talking to this other guy. So you've got to get the payment completed before they'll let you back in the course, and there's probably some deadline past which they won't do that. Okay? Word to the wise. Okay. Let's get on with class. So any questions on anything? It doesn't have to be the differential equation part, how the course is going to run, any of that. Okay. So we just barely got started in 1.1. We got our definition of a differential equation, but we ran out of time before we got to talk about how we classify differential equations. There are three main classifications. Let me get my pen set up. This is such a pain in the neck. Okay. Three main classifications. Okay? You can classify by type. You can classify by order. And you can classify by linearity. Okay. Now, we'll go over each one of these, and I'll give you the various levels within these classifications, okay? We'll hit those. So the first one here is classification by type. Two types, okay? We're only going to worry about one of them. Ordinary differential equation and partial differential equation, okay? And this will be called ODEs, and this will be called PDEs. Sorry, PDEs. Don't worry about PDEs. I don't think we'll do anything in partial differential equation, but if we do, it'll just be in passing to get to something else. Basically, we're going to focus on ordinary differential equations. So we'll occasionally use the word ordinary, but most of the time, if we say differential equations, I mean ordinary differential equations. So quite often, DE will just stand for differential equations, and you'll understand that's referring to ordinary. Okay. Now, here are some examples of ordinary differential equations. Okay? These are ODEs, ordinary differential equation. dy dx plus 5y is equal to e to the x. Okay. Now, it's an ordinary differential equation. What makes it ordinary? These are ordinary derivatives. You see? dy dx is an ordinary derivative. Okay. Now, here's another one. Oh, and by the way, I was thinking not of doing this, but now, since we got it written down here, I'm going to tell you a few other things. First, the orders. Now, we'll come back and do order in a minute. But order is what level of derivative are you dealing with. This is a first derivative. So this is a first order ordinary differential equation. Okay. Linearity, what are we meaning with? Are all your derivatives and y values to the first power? Yes, they are. This is dy dx to the first power, y to the first power. Doesn't matter what the x's are. So this is a first order linear ordinary differential equation. Okay? Now, here's another ordinary differential equation. d2y dx squared minus dy dx plus 6y equals 0. Okay? Ordinary differential equation because these are ordinary derivatives. However, this is a first order derivative. That's a second order derivative. So this is a second order ordinary differential equation because this is second derivative here. That's what we mean by order. Okay? Is this linear? Yeah, this one's to the first power, that one's to the first power, this is to the first power. Now we also call this something else later. It's not important now, but we'll say this is a, goodness gracious, I'm going blank on it. Homogeneous, meaning it's equal to 0. That's not homogeneous because it's equal to the function of x. Okay? Don't worry about that. We'll deal with those later. Okay, but just to let you know. Okay, how about this one? dx dt plus dy dt plus is equal to 2x plus y. Okay, that is also an ordinary differential equation because these are ordinary derivatives. However, this is in more than one variable. Okay? Now, still first order. So in the order, it's first order. Both of those are first order. It's a little harder to say whether that's linear or not. It sure looks like it is, but you have, and it is, but you have three variables. One independent, two dependent variables. Okay? X depends on t, y depends on t. So, yeah, it's linear, but we won't be worrying with those right now. Okay? So, those are all examples of ordinary differential equations. Well, what are partial differential equations? Now, Matt, I know you've had, and both of you have had Cal 3, right? Yeah. And we did partial derivatives then. So a partial differential equation will have partial derivatives. So if this was partial u with respect to x plus second partial of u with respect to y is equal to 0. By the way, this is a well-known partial differential equation, a PDE, a second order PDE, because both of these are at the second order. Okay, this is actually Laplace's equation, okay? That is a homogeneous equation. The derivatives are equal to 0, okay? So that has a special name. It's Laplace's equation, okay? Here's one. d2u dx squared equal d2u dt squared minus 2 the partial of u with respect to t. Okay? That obviously is a PDE, partial differential equation. Okay? Now, this also is a special type of equation. What surprises me is they have that with respect to x and then t. But I'll tell you, this is a form of a wave equation. Okay? But we won't go any further than that. Don't sweat it. We're not going to do any partial differential equations. But in case you see them, those are partial differential equations. U obviously is a function of x, so you have two independent variables, x and t, and u depends on x, and u also depends on t, and that is a special kind of a wave equation. It's a second order, and it, in a sense, is linear, but you got multiple variables, so we won't do much else with that. And here's another partial differential equation. Partial of u with respect to y is equal to minus the partial of v with respect to x. Okay? That's a special condition. It's a partial differential equation. First order, linear, so to speak, two dependent variables and two independent variables. U depends on y, v depends on x. It's not clear whether u depends on x or v depends on y. Doesn't really matter. We'll deal with that. Don't sweat these though, because we're not going to do any partials to speak of. We may have one pop up and just talk about it a little bit, but most of what we're going to do, ordinary differential equations. Okay. Now, a little bit of, I really don't know, there's a part of me wants to start over, but another part of me says, let's leave these things here and go from here. This just takes so long to erase. Okay, it's getting there. Okay, done. Okay. A little bit on notation. Leibniz notation basically is this, dy dx. Good old Sir Isaac Newton didn't use this notation. This came from Leibniz. In fact, that's about one of the main reasons Leibniz has any claim at all. He did use a different notation from Newton. Maybe he copied other things from Newton, but he came up with his own notation. Maybe he didn't. We don't know. d2y dx squared. Leibniz notation. d cubed y dx cubed. Leibniz notation. First order, second order, third order. Ordinary different. Those aren't equations that don't have an equal sign in them, but that's the notation. Now, we sometimes use the prime notation. Y prime, Y double prime, Y triple prime. Okay. Now, the only problem with this notation, you have to be pretty clear that there's only one independent variable and you know what it is. Remember those that had dx's and dt's or dx's and dy's? You really can't use the prime notation then because it's not clear which of these you're taking respect to. But if your whole problem you're only taking respect to a single independent variable, then you can use the prime notation. It's a lot simpler to write, easier to write, but don't use it if it's going to be confusing, okay? All right. If we go back, now I'm wishing I hadn't erased the board. dy dx plus 5y equal e to the x. That's that first equation we had before. How can we write that in prime notation? Y prime plus 5y equal e to the x. That's it. Second one, second derivative of y with respect to x squared plus or minus, sorry, it doesn't really matter, it's just a make-up problem anyway, minus dy dx plus 6y equals 0. What would that be? Y double prime minus y prime plus 6y equals 0. Especially when you're dealing with linear equations, one variable, that's a lot neater. A lot easier to fiddle with, and later on both of these, we'll use certain techniques, and the prime notation, as long as there's no ambiguity, that usually says it best and makes it easier to go from. Okay. Now, another thing on prime notation. What in the world would you do with this? D fourth y dx fourth. What would that be? Okay. You mean do 4 little tick marks? Okay. But be careful on that. Put it in parentheses. That means the fourth derivative of y with respect to whatever your variable is, in this case x. Okay? Don't do y4 that you think that's y to the 4th power. You have to put it in parentheses if it's the 4th derivative. And most of the upper level derivatives past y prime, y triple prime, you do in parentheses. That means derivative. If it doesn't have the equations there, you mean power. Okay, so do that. And from any beyond that, you do y to the n. Okay, that's the nth derivative of y, whether this is y to the nth power. Okay, you have to put parentheses around. Okay. No, although less convenient to write and to typeset, the Leibniz notation has advantages over prime notation in that it clearly displays both the dependent and independent variables. And if you have anything extra in there, you really need to identify what is what. You know, it's like if you had dx with respect to t and dy with respect to t, well, that might be okay. But if you had dy with respect to x and dx with respect to t, don't use the prime notation because you got 2 independent variables. It's not real clear what you mean. Okay. Now, you should be aware that in physical sciences and engineering, which maybe some of you are going to, Newton's dot notation, and that's derogatorily referred to some as the fly-speck notation, is sometimes used if you're talking about with respect to t. So if you had something with respect to t, I don't have anything on the board now, but if I had dy dt, Newton called that y dot. Second derivative with respect to t. Where if he did it with respect to x, it was y prime. So you get problems there, and the dots are, you say, is that a dot or is that a mark on the page? You know, there are some disadvantages. Okay? Now, I have another example here. d2s dt squared. That would be s double dot. In Newtonian notation, generally we're not going to use dot notation, so, but just in case you ever run into it, there it is. Now, partial derivatives, on the other hand, use subscript notation, but since we're not really going to do those much, I'm not going to spend a lot of time on that. But I'll ask you, do you remember how that worked? Just as an example. That's this one that we had before, d2u dx partial with x squared is equal to second partial of u with respect to t squared minus 2 partial of u with respect to t. Yuck. Okay. Using the subscript notation, that would have been u sub xx, goodness gracious, this is aggravating, is equal to u sub tt minus 2 u sub t. Okay? Now, don't sweat it. We're not doing that much of them, but just to remind you, when you did partial derivatives, remember you let those do like that, you know, the subscripts. Now, again, we're not going to mess with them, but remember, if you had taken the first partial with respect to x, but then the second partial with respect to t, then this would have been d2u d t dx. The one that you did first is on the right and the second is on the left. Okay. But when you do these, the one you do first, that would have been u sub x sub t. Because in this notation, subscript notation, the one closest to the u is the one you did first, and the one that's further from it you did second, or third, or whatever. So here they're in one order, and here they're in the other order. But don't sweat it. We're not doing these. But that was just a reminder of stuff we have done before. Okay. Now, that is classification by type. Okay? So I'm going to erase all this again. I thought I would. And now we're going to move to order. Let's get in the order here, okay? Order in the classroom, okay? Okay, your type was ordinary and partial, and usually if we ever use it, we're going to do ODE and EDE and PDE, but generally we're not going to do much partial at all. So when we talk about differential equation, we're meaning ordinary differential equations. Okay? Now, the old text used to specify that first course you had was ordinary, and then if you did advanced test, it would be partials. So let's now go to order. I've already introduced you to this. The order of a differential equation, either ODE or PDE, but we're going to stick with mostly ODEs, is the order of the highest derivative in the equation. Okay? Now, going to do a little mix up here. Here's d2y dx squared plus 5 dy dx cubed minus 4y equal e to the x. They did want to throw something squirrely in here. What's the order of that differential equation? Second, absolutely. That's the maximum derivative you're taking. Second derivative here. What does that represent? A first derivative cubed. That's still a first derivative. So its order of that term would be first, but the maximum is the second. So this is a second order differential equation. Ordinary differential equation, but this is not a linear differential equation because one of your derivatives is raised to a higher power. Okay? Derivative or the function itself. Now the x, the independent variable, can be raised to any power it wants to. That doesn't affect. It's only the y's. This y is to the first power, the second derivative to the first power. This y is to the first power, but the first derivative is to the third power. That keeps it from being a linear equation, makes it a third order different. I mean, not third order. It keeps it from being linear. I'll put it that way. Makes it a cubic in its first derivative. That's different from the order. Okay. Very good. Okay. Now, here's just a little, I don't know what you call it, kind of splitting hairs somewhat. If you remember back in Cal 1, we called these derivatives. First derivative, second derivative. That's what determines the order. Okay. But we call these differential equations. Well, back in Cal 1 and after Cal 1, a differential was usually written with the d's separated. Okay? In other words, here is an equation. M of x, y. That means this function is a function both of x and y, both independent variables, times dx plus n as a function of x and y, independent variables. dy is equal to, say, 0. Okay? Now, that's an ordinary differential equation because these are ordinary differentials. These are differentials written like this. Those are derivatives when they write them like that, but we don't call them derivative equations, we call them differential equations. But these are obviously, this makes it a differential equation. It's ordinary because these are d's, not partials. First order because the most you can get out of that is a dy dx if you divide it both sides by dy, which you don't usually do. So that would be first order, and that would be linear because this isn't squared, that's not squared. Okay. So this would be another way to express a first order ordinary differential equation, linear differential equation. And we do write that in certain circumstances. The rest of the time we do it like that, which you might say should be called derivative equations, but we don't. We call them differential equations too. So that is also a ordinary first order linear differential equation. Okay, because it really looks like it's got that. Okay. Now, what if this m of xy were something like y minus x? That's some function of x and y, and this is times dx plus This other n of xy really doesn't have any y dependence. It's just 4x dy. And if that's equal to 0, this would be an ordinary first order linear differential equation. Okay? And we'll do certain things with those, and they really make for an ease of doing certain types. Okay. Here's another differential equation, and we're going to use the prime notation here. Y prime, by the way, to remind you, y prime is, in this problem, dy dx. Okay? Okay. All right. Now let's take this equation we just did. I'm going to change that slightly and make it y dx minus x dx plus 4x dy equals 0. All I did was distribute the dx in the parentheses, basically. Okay? Now, the next thing I'm going to do is divide every term by dx. And most mathematicians, it makes your skin crawl to say dividing by dx, because that's part of a thing. But, yeah, let's see what happens. What do we have now? If you divide this by dx, it's still 0, by the way. So this would be 1. So this would be y minus x plus 4x y prime dy dx is equal to 0. Okay? Now, you'll notice that's what they have in a slightly different order. In fact, a very different order. They rearrange this to be 4x y prime plus y is equal to x. Okay? And again, that is another way to express this. Okay, there your mxy is this, but you can rearrange it there. Because we always assume that dy dx is your y prime, and so you can divide by dx. Here they go away. I didn't draw a line through. Those become 1s, and dy dx becomes y prime. Okay. Just different ways you can write these. Now, in symbols, sometimes we express an nth order ordinary differential equation in one dependent variable in the following way. Okay? Still doing by order. So here's the way. F of x, y, y prime, y double prime, y triple prime, oops, dot, 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 comma, y to the nth. Okay, this is a ordinary differential equation because we don't write partials. We don't write partials in these notations, the prime notation. So this guarantees it's an ordinary differential equation. There's nothing you can tell here about the order. No, I'm sorry. The order you can tell is the nth order ordinary differential equation because it depends on the y, the nth derivative of y. So it's the nth order. You can't tell anything about the linearity unless you saw what that function was consist of. If it had a term like this to the third power, yeah, that would be a y prime, but it doesn't know whether it's to the first power, second power, 14th power, or whatever. So you couldn't tell the linearity from that notation. You can't tell it's ordinary because you don't have time notation with partials. And you can't tell the order because it's the maximum derivative of y. Okay. Okay. How many variables does that have then? Well, from here, you go first, second, third, fourth, to the nth derivative. So that's n there. Then you have the y to the 0th power derivative, in other words, the function itself. That would be n plus 1, and x is n plus 2. So you have n plus 2 independent variables in that notation. Okay? Which is quite a few variables. Most of the time we're not getting that big. Okay. Trying to hit high points, so I'm going too slowly. Okay. Now, what if you didn't want some unknown function, capital F, there? Here's another way you could express that one. Now, what I'm going to do for now is just erase this that's in the way. It may come back later and erase more. But for right now, I'll just erase this because it is in the way. Okay. Oh, man. All right. You could write this way. Okay? This term here is the same as dny dx to the nth. Okay? And we could say this is equal to some other function. Why is this any better? Well, not necessarily, but you could say little f, and then this little f depends on only x, y, y prime, y double prime, y triple prime, dot, 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 up to y to the n minus 1. Okay. Because you pulled this one out, now that derivative, the nth derivative of y with respect to x n times, okay, that you can set equal to some lower function, say lower function, one fewer independent variable, little f. And you know, that's how we used to do it, remember? When you took a derivative of this, sometimes you call it capital F. Because when you integrate capital F, that was, we did that kind of stuff with it. So don't sweat this much. It's going to be a while before we use it. When we do, hopefully it'll be a little more obvious. They love to start these sections and even the first chapter with a lot of sort of hocus pocus, you know, nomenclature, you know, things about, and sometimes you get bogged down in it and you lose the meaning of it. Okay, so don't sweat it too badly. We will get there. Okay. We call that little f the normal form, real value continuous function, of the other form, which was the capital L form. Okay. To represent first and second order ordinary differential equations, for example, okay. Let's go on to linearity. So let's erase all this except just what we need. All right. Now, goodness, this eraser is slow. Okay. Goodness, this is slow. Okay, finally. I may have to go and clear my head one more time. I've been trying not to. Goodness gracious, I'm having trouble breathing. Now, the hoarseness that comes from going to a basketball game Saturday night, I yelled too much and got my voice hoarse, but my head's clocking up on me now. I don't know what that's about. Let's move to linearity, classification by linearity. I hope I've already given this away. Basically, it's either linear or nonlinear. That's all we're caring about. Linear or nonlinear. So basically, is every y and derivative of y, or whatever your dependent variable is, to the first power, not to the first degree, to the first power. If it is, it's a linear differential equation. If any one of them is squared or cubed or anything other than first power, then it's nonlinear. Okay? So, here's some examples here. Here is sort of a classic expression of a differential equation. Okay? It's an nth order ordinary differential equation if this. A sub n as a function of x, d, whoops, yeah, okay. Wow. dn y d x to the n plus a sub n minus 1 is a function of x, d to the n minus 1 y d x to the n minus 1. Plus, thank you, they're not going to do too many of those. Then you finally get down to a sub 1, it's a function of x, d, y, dx, plus a sub 0 as a function of x, y, and set all this equal to some function of x. Okay? Now, frankly, I would have rather written this in prime notation. This would have been y to the parentheses n prime, y to the parentheses, all the so such to say. This would be y to the parentheses n minus 1, and that would be y prime y dx. It would have been so much easier to write, but just since they wrote it this way, I wrote it this way. If every one of these derivatives and the function itself y are all to the first power, that's a linear differential equation. If any one of those had been squared or cubed or even a fractional power, okay, like to the 1.2 power or to the square root or anything else, those are all nonlinear. If they're all not to the first power, they are nonlinear. If they all are to the first power, they're linear. Okay. Nonlinear ordinary differential equation is simply one that is not linear. Nonlinear functions of dependent variable and its derivatives, such as sine y or e to the y, cannot appear in a linear equation. Okay, let's do example 2. I think I can erase all this. Please let me erase it all. Okay. Example 2. Here's some equations. Here's the first one. Y minus x, seems like we've seen this before, dx now. You tell me what your book, do either of you have books yet? Oh, you do. You see where I'm writing example 2a? Y minus x dx plus 4x. I can't read what was originally written there. What was it?
4x dy equals 0.
Okay, you didn't have a y in there. 4xy?
No, sir.
Okay, yours has been corrected. That's what I did. I scratched out the y. What they first wrote here was this. Okay? And they said that's a linear first order ordinary differential equation. It is not. Okay? The reason it's not is here you have a term that has both a y and a dy. That then would have to make it second order. Okay, so your book is correct. Scratch the y. If you get this paper copy and it has a y in there, cross it out. That is now a linear first order ordinary differential equation. Okay? This one. Whoops. Y double prime minus 2y plus y equals 0. Now, is that what's in yours? Or is that 2y, y prime?
2y plus 1.
2y plus y. Okay, minus 2y plus y. Okay, I won't argue with them. That is a ordinary, linear, second order differential equation. Why write it like that, though? See, that's the thing I couldn't figure out what they were getting at. Why have a minus 2y plus y? That would be y double prime minus y equals 0. Why have two y terms in there? I thought that maybe one of those was supposed to be prime, but your book doesn't have a prime on either one of them? Okay. I still think they meant to, but they didn't. That's the same as the thing below. But if one of those was a prime, like minus 2y prime plus y equals 0, that still would have been a second order linear ordinary differential equation. Okay? So, there's no reason to have two terms with y alone in them. Okay, here's another one. X cubed. This one I think they wrote right. Okay? d3y dx cubed plus x dy dx minus 5y is equal to e to the x. Okay? That is a ordinary, those are all the derivatives are ordinary derivatives. Third order, because the maximum derivative is third derivative. Linear, because each of your y terms, your derivatives of y and the y itself, are to the first power. And ordinary differential equation. So that's an example of a linear ordinary differential equation. Now, This one, 1 minus y, y prime, plus 2y equal e to the x. That is not a linear ordinary. It is an ordinary differential equation because the prime notation indicates ordinary derivative, okay? It's not linear because even though if you multiply through, this would be a y prime and this would be a minus y times y prime, you have two y's in one term. One's a y, one's a y prime, but that can't be linear. That's linear, that's linear, this term right here is not linear, okay? If you have a product or a power of y's in there, not linear, okay? This one, d2y dx squared plus sine y is equal to 0. Not linear. This is second order, linear term here, ordinary, but this is a nonlinear expression of y. Now, if that had been a sine x over here on the outside, no sweat. Doesn't matter what that function of x is, but your y's have to be first power, no nonlinear functions. Sine y is not a linear function. It's a nonlinear function. So that's the nonlinear, ordinary, first order differential equation. Okay? This one, d4y dx to the fourth plus y squared is equal to 0. Ordinary differential equation, yes. What's the middle thing? I'm going blank on it now. Yeah, ordinary was the type. It's not. It's a fourth order. That's what I was saying. It's ordinary in that you don't have any partials, but it's a fourth order because the maximum derivative is fourth. Now you see in this notation we do right. In Leibniz notation, d4y dx fourth, that's fine. It's only in the prime notation that you put 4 in parentheses. Okay? But then the y squared, that is not a linear term. That's a squared term, so it can't be a linear in y. Now, if that would have been is equal to x squared, no sweat there, because it's only the y's that determine the linear and nonlinear. Okay. Now, one other piece of nomenclature, okay, and that's solutions. And they stated before, I'm going to take the word for it, one of the goals in this course is to solve or find solutions of differential equations. In the next definition, we consider the concept of a solution of an ordinary, not partial, ordinary differential equation. And here's that definition. Okay. The solution of an ordinary differential equation. Any function, we're going to call it phi, defined on an interval I, and possessing at least n derivatives okay, that are continuous on I, on that same interval the function was defined on, which when substituted into an ordinary nth order ordinary differential equation, which, when substituted into an nth order ordinary differential equation, why didn't I call it ODE? We'll just call it DE for differential equation, reduces the equation to an identity, then that's said to be a solution of that differential equation. On that interval. I. Okay. Okay. Oh, man. In other words, a solution of an nth order ordinary differential equation 4 is a function phi. Where's equation 4? I've lost it. It's on the previous page, page 3, bottom of the page. Okay. Is a function phi that possesses at least n derivatives and for which that's true for all x's on the interval. Okay. We say that phi satisfies the differential equation on I. For purposes, we shall also assume that the solution phi is a real valued function. Okay. In our introductory discussion, we saw that not going to mess with that yet. We'll get back to it. Ordinarily, it is convenient to denote a solution by alternative symbol y of x, not phi of x, whatever you want to call it. So let's again mention what in the world we mean by this interval I. You can think solution of ordinary differential equation without simultaneously thinking interval. You cannot. They go together, hand in glove. The interval I in the definition is variously called the interval of definition, the interval of existence, the interval of validity, or the domain of the solution. And it can be an open interval AB. Okay. Let's look at example 3. I think we just barely are going to be able to have time to do it, but let's try to get that done. Hopefully we can. Verify that the indicated function is a solution for the given differential equation on the interval minus infinity, infinity. That's the whole real number line. So here's the differential equation. dy dx is equal to x times y to the 1/2 power. Okay? That's your differential equation. Okay, let me just tell you. It's an ordinary differential equation because it's a dy dx, not a partial. It's a first order ordinary differential equation because the maximum derivative is first derivative. It is not a linear differential equation because y to the 1/2 is not a linear function of y. It's a square root function, not linear. Okay, just to let that go. Well, here's what they suggest a solution is. Y is equal to 1/16 x to the 4th. Now, how do we verify that that is a solution for this equation? Well, we've got to do everything that this equation says to do with y, you have to do it, okay? For instance, here, you take a derivative of y. We know how to do that, don't we? So let's do dy dx. What is dy dx for that variable y? What would it be? Take a derivative of that. Not 1/2, 1/4. 4 times 1/16 is 1/4. X to the third power. Perfect. But we also have a y to the 1/2 here. So we also need to find out what y to the 1/2 is. If y is 1/16 x to the 4th, what is the square root of y? Okay, if this is y, what is the y to the 1/2, which is the square root of y? That would be what? What's the square root of 1/16? 1/4. And what's the square root of x squared? I mean, x to the 4th. X to the 2nd. Very good. So now we know what dy dx is. Now we know what y to the 1/2 is. Let's plug those in and see what we get. Dy dx, we see, is 1/4 x cubed. That's the left-hand side. Supposedly, we don't know this is true. Let's see if it is. That's equal to x times y to the 1/2. That would be 1/4 x squared, right? Well, let's see if that's true. 1/4 x cubed, sure enough, is equal to 1/4 x times x squared is x cubed. Yes, that's the solution. You reduce that to be an identity. Therefore, that is a solution. Now, just to keep from scaring you too much or worrying you too much, but just to let you know it's happening, that may not be the only solution. We're going to spend a lot of time trying to figure out if there are any other solutions. But that did tell us that was one. Now, how did we get it? We don't know. They just gave it to us. But we did verify it's a solution. And I believe we just run out of time, haven't we? So we'll pick up on the B part of example 3 next time. Okay? So let me give you a few homework exercises. Exercise set 1.1. Do any of the odds 1 through 7. Do number 9. And let's stop there. No. Try to do 11 or 13. It's like the one we just did. Okay? And we'll hold off and do the rest of those later. Okay? All right. Have a good weekend. I say that every time we meet, don't I? Okay. But yes, first time I'll say we'll see you Monday. Okay. Good deal. All right. You are not in the physics class, are you?
I am.
You are. They're going to move in here. Oh, the next one. Okay. Okay. I was going to say the next class that used to be there is moving this way.